In this lesson, I'll show you how to find the equilibrium partial pressures when we are given the equilibrium constant and initial partial pressures. The question reads, consider the reaction below. A reaction mixture at 25 degrees Celsius initially contains a partial pressure of iodine equaling 0.100 atmosphere, a partial pressure of chlorine gas equaling 0.100 atmosphere, and a partial pressure of ICl equaling 0.100 atmosphere. Find the equilibrium partial pressures of I2, Cl2, and ICl at this temperature. Much the same way we did with equilibrium concentrations, we'll be creating an ice table here to organize our work. So let's go ahead and do that. I'll rewrite the reaction, I2 plus Cl2, and this yields 2 molecules of ICl. We've been given the initial pressures, and I'll create 3 rows, I, C, and E. I'll write in the pressures for each. No need to write the units. And now we are looking for the equilibrium pressures. Before we can do that, let's see which direction this reaction will take place in. That can be calculated by finding the reaction quotient, represented by QP. So let's take a look at this reaction. We have ICl and 2 molecules of that, ICl and 2 molecules of that, so we raise that to the power of 2 over these 2 partial pressures. So the pressure of I2, and that's being raised to the power of 1 because of a coefficient of 1, and same with this. So let's substitute those values really quickly. 0.100 raised to the power of 2 over 0.100 times 0.100. Mathematically, one of these will cancel out with the one at the top, leaving us with, technically, 1. That will cancel out with this one then. So because Q, which is 1, is less than Kp, when Q is less than Kp, the reaction shifts to the right. Okay, now we can concentrate on finding the equilibrium pressures. I'll start by setting the change of one of these molecules equal to x, and it doesn't matter which one you set equal to x. If I create a ratio comparing this to this molecule, it's a 1-to-1 ratio, so that's x as well. If I compare this to the reactants, we have a 1-to-2 ratio, so it's 2x, and since you're comparing reactants with products, you negate the number. So since this is currently positive, it becomes negative 2x. Okay, now to find E, I'll add these up, these, and we end up with 0.100 plus x, 0.100 plus x, and over here, 0.100 minus 2x. Let's write down the equilibrium expression, Kp. We're dealing with pressures here, and using the same scheme over here, and I'll replace ICl squared this time with this expression being squared, because we're no longer looking at the initial, we're looking at the equilibrium. That's being raised to the power of 2. And at the bottom, we have these 2. They're the same, so I'll just raise them both to the power of 2. I'll replace Kp with what they gave us in the question, 81.9. Lucky for us, this is easier than the other questions that we've done because we can simply square root both sides, and by square rooting both sides, mathematically, this power and this power of 2 go away. So we have the square root of 81.9 is equal to 0.100 minus 2x over 0.100 plus x. Also be mindful, and we've discussed this in the past with other examples, that when you square root a number, 81.9 in our case, you'll end up with a plus minus value. So the root of 81.9 can be either plus or minus. So keep that in mind as you answer. Next, I'll multiply both sides by the denominator to clear out the denominator of this fraction. So this cancels out with that, and what you do on one side, you do on the other side. Just like that. And also, like I mentioned, this can be plus minus. Let's use the positive version just for simplicity's sake first. And if it happens to be the right version, then we don't have to worry about the negative version. So on the left side right now, we have this expression. On the right side, we have only the top part because the bottom part has been removed. I will now expand, meaning multiply this factor to these two. I have 0.100 being multiplied to the square root, the positive version of this, of course, plus the square root of 81.9 times x. It's being multiplied to both of these terms, and that is equal to 0.100 minus 2x. I'll collect like terms, so I will bring this term to the left side and this term to this side. Watch what happens. Negative 2x minus, because we're negating it now, we're bringing it over, the square root of 81.9. And on the left side, we have this minus that. All we're doing here is basic math, coupled with, of course, chemistry. So on the left side, we have 0.100 times the square root of 81.9. That covers the left side after we subtract by 0.100. We have 0.804, let's include a few more numbers, 98. And on the right side, I do realize there's supposed to be a negative here. I almost forgot. Negative 2 minus square root of 81.9. And that gives us negative 11.049 and the x. To solve for x, we divide both sides by this number, and this cancels out with that, leaving us with what x is equal to. 0.80498 divided by negative 11.049, and we get a negative number. Now, normally this is something to panic about because negative x values often give us the impression that the answer is wrong. But let's see what happens if we substitute this value into x here, here, and here. If all of our numbers come out positive, then by choosing the positive version of the square root of 81.9 was the correct one to choose. And we don't have to redo all of the calculations for that negative version. So I'm going to take 0.100 and add it to the number that I found, and it turns out to be positive. In fact, I'm going to write that number down right now, 0.027, and one more significant figure. That's the atmosphere at equilibrium. And it's going to be the same thing for this because they're both the same. Let's apply this number into here now. So 0.100 minus 2 times negative 0.0728, and hopefully it's positive. It is. So we don't have to worry about redoing this calculation. 0.24 and to three significant figures, 6 atmosphere. And there you have it. That is how to find the equilibrium partial pressures using ice tables. If you would like to see another example, make sure you watch question 2 of this series, which will also be posted. We'll see you soon.